Hey, what's up YouTube? In this video, we're going to get some practice using those three operations we've been talking about in the last couple of videos. And we're going to do that by looking at an example. So in this example, we want to solve the following system of linear equations. Now recall that we proved in a previous video that applying any one of these three operations to a linear system results in a new linear system with the same solution set. So now we're going to use these three operations to solve our linear system, and in particular, we're going to use these operations to obtain a linear system with the following properties. So first, we'll want the first non-zero coefficient of each equation to equal 1. You can see already that our system does not have this property. Here, the second equation has the first non-zero coefficient equal to -4, and then in the third equation, the first non-zero coefficient is equal to 2. So clearly this system doesn't satisfy the first property. The second property we want our system to have is that if an unknown is the first unknown with a non-zero coefficient in some equation, then that unknown has a zero coefficient in each of the other equations. So for instance, since this is the first unknown with a non-zero coefficient of the first equation, property 2 says that we would need x sub 1 to have a zero coefficient in all the other equations. So we would need to change the second equation to make this coefficient equal to 0. And then finally, the third property we want our system to have is that the first unknown with a non-zero coefficient in any equation has a larger subscript than the first unknown with a non-zero coefficient in any preceding equation. So that means since x sub 1 is the first unknown in the first equation with a non-zero coefficient, we would need to get rid of this x sub 1 so that the first unknown with a non-zero coefficient of the second equation would have a subscript greater than 1, so it would have to be 2, 3, or 4. And then similarly, we would need the first unknown in the third equation with a non-zero coefficient to have a larger subscript than the subscript of the first unknown in the second equation. So once we obtain a system with these three properties, then we'll be able to express certain unknown variables in terms of other unknowns, and from there we can describe the solution set. So let's go ahead and get started solving this system now. So we have enough space. I'm just going to move the properties that we want to obtain up here and then write our system that we're trying to solve down here. Alright, now to get started, first notice that since the first equation has an x sub 1 term with a non-zero coefficient, property 2 says we need x sub 1 to have a zero coefficient in every other equation, just like we said before. So now we need to eliminate the x sub 1 term from the second and third equations. But since the coefficient of the x sub 1 term in the third equation is equal to 0 already, we only need to eliminate the x sub 1 from the second equation. So we just need to get rid of this x sub 1 here. Now to do that, we'll use the third type of operation to replace the second equation with the sum of itself and 4 times the first equation. And we multiply it by 4 so that these will cancel out and we'll have a new equation with no x sub 1 term. Now when we multiply each term of the first equation by 4, we get this new equation, and then when we add that to the second equation, we end up with this new equation where this new equation doesn't have an x sub 1 term. So now we replace the second equation with this new equation, and we get this new linear system where this linear system has the same solution set as our original system, because we got this new system by applying one of our three operations, specifically the third operation. Now from here we can focus on solving this linear system. Now notice that this new system has x sub 2 as the first non-zero coefficient of the second equation. So property 1 says that we need to make this coefficient equal to 1. To do that, we'll use the second operation to multiply every term of the second equation by -1/3, and that will give us our new equation 2. Now when we multiply the second equation by -1/3, we get this new equation 2, where the x sub 2 term has the coefficient equal to 1. Now replacing the second equation with this new one, we get this new equivalent linear system. And we'll continue by solving this new system. Now you can see that this system doesn't satisfy our third property, since the x sub 2 term is the first unknown with a non-zero coefficient in the third equation, but the subscript 2 for x sub 2 is not larger than the subscript 2 in the preceding equation. So we need to eliminate the x sub 2 term from equation 3. To do this, we'll use the third operation to replace the third equation with the sum of itself and -2 times the second equation. Now when we multiply the second equation by -2, we get this new equation, and then when we add that to the third equation of our system, we end up with this new equation 3, where this new equation has a zero coefficient for the x sub 2 term. Now when we replace the third equation of our previous system with this equation, we get this new equivalent linear system, where now this system satisfies the third property. Now since we obtained this new system, by applying a sequence of operations to our original system, we know that these two linear systems have the same solution set. So for the sake of saving space, I'm going to move this new system up here and we'll go forward with this new system from here on out. Okay, so we said this new system satisfies the third property, but it still isn't the system that we want to obtain. It still doesn't satisfy the first two properties. To make it satisfy the first property, we need to make this coefficient for the x sub 3 term equal to 1. So we'll do that by multiplying every term of the third equation by -1/2. Then the coefficient for the x sub 3 term would be equal to 1. The coefficient for the x sub 4 term would equal -10, and the constant on the right-hand side would be equal to 1. So we get this new equivalent linear system, where this new system satisfies the first and third properties, but notice that it doesn't satisfy the second property, since the second property says that since x sub 3 is the first unknown with a non-zero coefficient in the third equation, then we need to eliminate the x sub 3 from equations 1 and 2, and then similarly, since x sub 2 is the first unknown with a non-zero coefficient in equation 2, that we would need to eliminate x sub 2 from the first equation. So we'll need to eliminate these terms here. And we can do this any way we like, but it's more efficient to work upwards, eliminating these x sub 3 terms, and then work to the left to eliminate this x sub 2 term. And the reason this way is more efficient is because it leads to less computations than, say, eliminating this x sub 2 term first and then the x sub 3 terms. And you can see how it's more efficient, because if we did do it this way, where we eliminated the x sub 2 term first and then the x sub 3 terms, we would have to replace the first equation with the sum of itself and 2 times the second equation to get rid of this x sub 2 term. And to do this would require 4 computations, 1 computation for each term that has a non-zero coefficient in both these equations, so these 3 computations, and then 1 extra computation for the constant on the right-hand side. So that gives us our 4 computations to eliminate the x sub 2 term of the first equation. And then from there we would have some new system where this x sub 2 is gone. And so then we would want to eliminate the x sub 3 term from the second equation, which would take 3 computations, because we would use this x sub 3 term to eliminate the x sub 3 term above it, meaning we would need to replace the second equation with the sum of itself and 2 times the third equation. So we would have a computation here, here, and here, which gives us our 3 computations, and then similarly for the x sub 3 term above, we would have the 3 computations, 1 here, here, and here. So that would have 3 computations there for a total of 10 computations. Whereas the method we're going to use will only take 9 computations, so we're going to do it by first eliminating these x sub 3 terms and then working to the left to eliminate this x sub 2 term. So eliminating each of the x sub 3 terms will still take 3 computations. So we'll have 1, 2, 3 for the first x sub 3 term, and then similarly 1, 2, 3 for the second x sub 3 term. So we'll get some new system where these x sub 3 terms are gone, and then from there we'll use this x sub 2 term to eliminate the x sub 2 term above it. And to do that we'll only need 3 computations because these x sub 3 terms are gone, so we won't need to compute anything there. We'll just have these 1, 2, and 3 computations needed to eliminate this x sub 2 term from the first equation. So our method will take a total of 9 computations instead of 10. And so you can see that this is more efficient, which is why we're going to use this method. So now we're going to eliminate this x sub 3 term, and I'm actually going to eliminate this one as well, all in one step. So we'll just combine these 2 steps together. So first, to eliminate this x sub 3 term, we're going to use the third operation to replace the second equation with the sum of itself and 2 times the third equation. So when we multiply the third equation by 2, we get this equation, and then adding that to our second equation, we end up with this new equation 2 where the x sub 3 term has been eliminated. So now we'll put our new equation 2 up here, and then in the same step we'll eliminate this x sub 3 term. And to do that, we're going to use again the third operation to replace the first equation with the sum of itself and -1 times the third equation. So when we multiply the third equation by -1, we get this equation here, and then adding that to our first equation, we end up with this new equation where the x sub 3 term is now gone. So now we have our new equation 1 and our new equation 2, and so we get this new equivalent linear system. Now finally with this system, the last thing we need to do is eliminate this x sub 2 term. So again, we're going to use the third operation to replace the first equation with the sum of itself and 2 times the second equation. So when we multiply the second equation by 2, we get this equation here, and adding that to the first equation, we end up with this new equation 1, where the x sub 2 term has been removed. So putting this new equation 1 into our system, we get this new equivalent linear system, where now this linear system satisfies all 3 of the properties that we wanted it to satisfy. You can see that the first non-zero coefficient in each equation is equal to 1, since the x sub 1, x sub 2, and x sub 3 terms here all have coefficients of 1. The second property is also satisfied, since any time we have an unknown that's the first unknown with a non-zero coefficient in some equation, that unknown has a 0 coefficient in each of the other equations. So here in the first equation we have x sub 1 being the first unknown with a non-zero coefficient, and x sub 1 has a 0 coefficient in all the other equations. Similarly, x sub 2 here is the first unknown with a non-zero coefficient for the second equation, and then the x sub 2's in the other equations are having the 0 coefficient, and then finally the x sub 3 term here for the third equation is the first unknown with a non-zero coefficient, and then we have the x sub 3 terms having 0 coefficients in the other equations. Now notice that these x sub 4 terms are never the first unknown with a non-zero coefficient in an equation. So in each of these, they're the second unknown in that equation, so that property 2 doesn't apply to them, which is why we can have the x sub 4 in each equation. And then finally, we have the third property is satisfied, since we have this diagonal line here, where the subscripts of the unknowns are getting larger. So we have the first subscript equaling 1, then 2, and then 3. So that the first unknown with a non-zero coefficient in any equation has a larger subscript than the first unknown with a non-zero coefficient in any preceding equation. So we have in fact obtained a linear system with the 3 properties above that we wanted. Now I'm going to include our original system and all the steps that we took to get to this point. So I'll move this down and then include the first 3 steps that we took, so you can see the sequence of changes that led us to get this new system, and also so that you can see that each of these steps, since we used one of those 3 operations that we talked about before, we know that this linear system has to have the same solution set as this one. So solving this system is the same as solving this one. And this system is much easier to solve because we can solve for each of these terms on the diagonal, the x sub 1, x sub 2, and x sub 3 terms on this diagonal line. We can solve for each of those easily in terms of x sub 4 by just adding these terms to the right-hand side of the equation. So by doing that, we get these 3 equations for the x sub 1, x sub 2, and x sub 3 unknowns. And so we know that any solution to our system is a 4-tuple of this form, where x sub 4 is any real number, and the x sub 1, x sub 2, and x sub 3 terms are these 3 equations based on the x sub 4 term. So this system has infinitely many solutions, and the solution set is given by this set here. And so we have our answer. And that's all for this video. Thanks for watching. I'll see you next time.